for everyone, and welcome to an introduction to astrophotography. Yeah, probably a very fascinating subject that all of you are very interested in. I've been lucky to engage with some of you as part of the NSC astronomy and astrophysics groups. And for the rest of you who haven't sort of interacted with me, I hope that this would be an interactive sessions. I've received some very interesting comments and questions, which I hope to cover as I go along. And then at the end of it, we also have a question and answer round. So we'll be covering, we'll try to answer most of your questions. And if you can't answer most everything, because astronomy is a vast subject, so I'm sure we'll have more sessions coming up. So with that said, let's begin. Okay, so what is astrophotography? I mean, astrophotography is such a fascinating subject, and it is as vast, I would say, as literally the universe itself. Because if you consider the scope, it is trying to photograph everything in the universe. Okay, and the universe, as maybe infinite, or even if it's not infinite, it's extremely large. So considering all that, the scope of astronomy is quite huge, and the scope of astrophotography is equally large. So it's a vast topic, and we will try to sort of cover as much as we can. When I think about astrophotography, I think of it as sort of equal parts science and art. Okay, so the basis of astrophotography is astronomy, and astronomy is a science. So in order to have good observation, you need to collect data very accurately. Okay, you need to analyze data very accurately. And once you're done that, you process that data. Okay, and when you process data, it can be for put to scientific use, or it can be used for artistic or aesthetic use. So this is where the artistic feature of astrophotography comes in the picture. So it's sort of equal parts science and artist, and I find that it appeals to a wide range of people, be they scientists or even people who are not associated with science, are drawn towards these beautiful images that we can produce from the depths of the universe. And in fact, my first sort of very quick topic will be on how astrophotography helped astronomy or astrophysics. We'll see that in the coming slides. The second point is it's a cure for aperture fever. Now, those of us who are stargazers, who do regular stargazing, would probably be aware of this jargon called aperture fever. But for the benefit of those, let me sort of explain what I mean here. So I started my engagement with astronomy way back when I was in school, and I got my first telescope, which was a small 3-inch scope. I got it from the Nehru Planetarium, and I was happy. I could look at the moon, I could look at Saturn, I could look at Jupiter, but I wanted to see more. Okay, so I went on and bought a 5-inch reflector. I then later on I got a job. I moved overseas. I could comfortably get an equatorial mount automated computerized telescope, which had an 8-inch aperture. So aperture here is the diameter of the mirror, and more bigger the diameter, more is the light collecting power. So you can see fainter and more distant objects. But as I started seeing fainter objects, I looked at the universe through better and better equipment. And I realized that there is a limit here, that even if you get the most largest telescopes and you try to look through it, you will not be able to see the universe in its full glory. You cannot see color, for example. And that's not a limitation of the telescope itself, but a limitation of our human eyes. Okay? Our human eyes during faint light cannot detect color. It cannot detect as much detail as something like a camera sensor would. Okay, so I realized rather sadly that my eyes can never see the color of the glorious Hubble telescope photographs. So that turned me towards astrophotography. In a way, it's a cure for not going for bigger and bigger telescopes. Even with smaller telescopes, even with modest sort of optical tubes, you would be able to get these amazing pictures. This is what I'll be talking about in the subsequent slides also. Third point, I mean, astronomy, it brings astronomy to the masses. I think anyone who's admires the photographs taken by the Hubble Space Telescope, okay, would, I think, acknowledge that, most likely their interest in astronomy and astrophysics grew because they started looking at these amazing, beautiful photos taken by the Hubble Space Telescope. So astrophotography, whether they're taken by the Hubble Space Telescope or even now, even taken by amateurs like me and people who are better than me, you can now bring astronomy to the masses. It really helps in the, for me at least, as a public outreach person, if I can explain something to the public, to the students by means of a photograph, I think it clicks better. So for me, as they say, the picture speaks 1,000 words. So it has helped explain me explain a lot of concepts of astronomy using some of the photos that I'm able to take. Lastly, it is challenging because as we'll talk about the challenges later, but it can be incredibly rewarding because you are essentially capturing light which left millions of light years. So if when you take a photo of the Orion Nebula, that's 1,500 light years away, or Andromeda, that's 2.5 million light years away, or even further, you yourself are able to gather these photons which started their journey perhaps even before the humankind existed on Earth. So it's, you're capturing ancient photons. So once you get the hang of it and you get it, it can be incredibly rewarding. Okay, so before we get into the sort of the main topic, I like to sort of touch upon this because yes, my interest is astrophotography, but it stems from my interest in astronomy and astrophysics. So everyone knows about the apple falling on Newton's head and Newton discovering gravity. And for 200 years, that was our understanding of how gravity works. And then came Albert Einstein, and in 1915, he proposed his general theory of relativity. And that gave us a completely revolutionary idea of how gravity works. So it was a very elegant theory. It was mathematical, but it had to be proved. And it was in the year of 1919, when there was a total solar eclipse, that Einstein's theory got proved. How? Because there were these astronomers who could go out and take photos of the solar eclipse. Why the solar eclipse? Because Einstein's general theory of relativity predicted that gravity should be able to bend light. Okay, according to Einstein's theory of relativity, any massive objects, it bends space, and any object which comes near goes in a curved path, including light. So if the sun, which is a massive object, can bend light, you should be able to see stars which are behind the sun or in the vicinity of the sun. Normally, you'll not see stars near the vicinity of the sun because the sun is too bright, except when there's a solar eclipse. So there was this very opportunity in 1919, in the May of 1919, and astronomers were able to take a photo of the solar eclipse, and they noted the position of the stars in the background. These are stars from the Hades star cluster, and it was known where the location of these stars should be and where they would be if Einstein's theory was correct. As it turned out that the stars were exactly where Einstein's theory predicted them. So this astrophotograph essentially proved Einstein's theory of relativity, and in doing so, changed the world, changed our understanding how gravity works and how time and space work. So this, according to me, is one of the more famous astrophotographs. So that's about the professional astronomers. Speaking about us, people like us, amateur astronomers, we have several challenges. So as Sir pointed out, it's a challenging hobby because you're trying to take a photo of something that's dark and that's out at great distance. If you want to do that, you require a very slow shutter speed. Okay, these are sort of optical terms I'll explain as we go ahead. But essentially, you need a very slow shutter speed. At the same time, you are trying to shoot from a platform which is moving, which is planet Earth. So this creates a very unique challenge. Normally, when you try to take a photo from a moving vehicle, so let's say you're traveling in a car and you try to take a photo of a tree outside, you'll find that the tree gets blurred. That's because the car is moving. So how do you overcome this? So this is one of the challenge. It gets difficult if the tree is in dark, it's at night. So but we overcome this challenge in astrophotography. So the second challenge, I think we all know. I think we try to look at stars from city locations, and we find that we can't see many stars. And astrophotography requires that you should be able to see stars. You should be in a place where it's dark. Unfortunately, these dark locations then are not very comfortable for humans, but I'll touch upon some of the locations that I've been lucky to visit and what I can share my experiences there. The third category, what we call noise. So noise is not sound noise, it's electronic noise. Okay, if you've seen old photographs, okay, you'll find that they're not very sharp, and you'll find they appear grainy. So that graininess, okay, is what we call noise in sort of this astrophotography jargon. So that is a big challenge. Why? Because we are shooting objects which are very faint. Okay, so again, we will talk about this in detail also. And as you'll probably guess, when it comes to deep sky astrophotography, it can get incredibly complex and expensive. Okay, so I don't want to discourage a lot of people who are getting into the hobby. Yes, you can get into astrophotography and you can do amazing things. But at one point, it simply starts getting very complex and very expensive. But that's later. That we can talk about how that can be overcome as well. And the last one is a recent thing. It's actually number of artificial satellites is increasing. Okay, and especially now with SpaceX launching Starlink satellites, will make it's a good thing that the internet will be available throughout the Earth. Okay, so there's no need to have ground cables supplying internet. Everyone on planet Earth would have access to the internet. But then the downside of that is that when astronomers, amateur astronomers, try to take photos of the night sky, we see these trails, which are essentially satellites crisscrossing our astrophotography images. So that's
Hello.
hello, yeah.
Sir, I have a question. Sir?
All right.
Yes,
So
how only Starlink satellites can affect? Other satellites can also affect astrophotography.
I'm sorry. Is that question? Can you repeat that?
How only Starlink satellites affect astrophotography? There are many satellites.
Yeah, that's the whole problem, because it's not a few satellites. The plan is to launch thousands of satellites. So it's a constellation of satellites. So the plan is that they cover, and they'll be in low Earth orbit. They'll not be high Earth orbit as well. So lower Earth orbit, there's a greater chance of cameras catching these Starlink satellites very easily. In fact, they've already been captured in photographs. There are ways to remove them at the cost of reducing the quality of the image a bit. Yeah, but it is a bit of a issue. Okay. So yeah, Starlink is one of the issues, and people are talking to Elon Musk, and then he has some plan to paint the satellites dark so they don't reflect light so much and all that. So there are some things being worked about, but it is a concern at the moment. Yeah, but I don't want to make it too large than what it is. Okay, so we'll talk about it later in the session also. All right, so okay, so there are some important concepts, they might look foreign, or they may look difficult for someone who's not used to this technical words. So I'll just briefly talk about them. So there's something called signal versus noise. Okay, so the signal is a light from these distant objects that we want to capture. So if I'm capturing photo of, let's say, the Orion Nebula, okay, so within that signal, apart from the light from the nebula itself, I'm also capturing light pollution from my city, from the place where I'm capturing the photo. The camera, which is capturing the photo, also has something called thermal noise. Now, what is thermal noise? Now, as the temperature rises, the graininess of the image increases. Okay, so this is an inherent property of electronics. Okay, because we are capturing signal, which is essentially converted to an electronic signal, and the camera electronics is also a kind of signal, and there is also always a bit of random noise or random electrical signal which is circulating within the electronics of the camera sensor. So this is what we call noise. It is random. It is not it doesn't have a specific pattern. It is a random thing, and it always is there. It is generally a property of temperature. What do I mean by property of temperature? Higher the temperature, more is the thermal noise. That's why it's called a thermal noise. And I can reduce that by maybe going to a place which is colder, or maybe even cooling my camera. So we'll see how that is achieved. And there's something called false light, which is introduced while reading the pixel of the sensor. So this is called readout noise. So the camera, when it records the signal, okay, that time also it can make an error because it's an electronic circuit. These are typical things that happens in electronic circuits. Sometimes they can have an error. Okay, so this is what I call noise. There's something called distortion. So the distortion is if the atmosphere is turbulent, okay, and you try to take a photo, it is like trying to take a photo of pebbles under a pond. If the water is flowing, okay, your picture of the pebble will not be steady. So think of an atmosphere as a pond where there's constant movement. Even though we don't see air, especially in summer, you may find there's turbulence. Okay, so that turbulence can cause atmospheric distortions. Also, there's something called, also there's distortion which is introduced by the optics. So if I'm using a telescope or I'm using a camera lens, and there's some limitations. So these limitations also cause what you call distortion, which I listed a few here: vignetting, chromatic aberrations, spherical aberrations. So if I want to take a photo of star, it will not come out like a star. It will look like a comma. Okay, so or it will look like something like a comet. So that is a distortion of the image. So this is a problem with the optics, the telescope, and there are ways to resolve this also. And so we want to maximize the signal, okay, and reduce the rest of the things, reduce noise, reduce distortion. So we'll see how that is done in astrophotography. So to reduce light pollution, we need to move away from the city. So I know everyone is comfortable with sitting in a city and having access to internet and TV. Unfortunately, for astrophotography, you need to travel to a dark location, and unfortunately, dark locations are generally not very comfortable. So this is what we call a bottle scale. It starts from 8 or 9 and goes up to 1. Okay, the 1 bottle scale means it's an excellent dark sky. Okay, that's the best dark sky you can achieve on planet Earth. On the other scale is the heart of the city. So if you're staying in Mumbai, okay, or any big city, Delhi, for example, okay, or Bangalore. I've stayed in Mumbai, I stayed in Hyderabad, I stayed in Bangalore, all these, I stayed in Dubai. So these places are very light polluted. So they are on bottle scale 8 or 9, extreme left. So you'll not see anything there. Okay, as you move away from the city, okay, maybe bottle scale 4. Okay, then you come to your villages. Okay, you realize when you move away from the city and move towards village, you'll see more and more stars. Maybe around bottle 4, you'll start to see the Milky Way. You should at least be able to see the Milky Way if you want to do some astrophotography. So this is a good indication as to what place you should select for astrophotography. In fact, you can find out, there are many applications that will tell you how deep or how dark is your sky and what is the bottle scale of your particular place that you stay. So I've been lucky enough sort of to visit some of these dark places. So as to stay in the United Arab Emirates, so as to travel away in the deserts. So deserts are away from the city, so that makes the sky darker. Okay, but the ultimate are the mountains. So the view from the Himalayas is extremely clear. Okay, why? The two things. One is that you're away from the city, so there's less people staying there, there's less light pollution. Also, you are at a higher altitude. Because of the higher altitude, the air is thinner. And since the air is thinner, there's less turbulence. So mountains are the best places. And the higher up you go, the better astrophotography you can do. That's the reason the Hubble Space Telescope is in space. It's in orbit, okay, above all the turbulent atmosphere of Earth. Okay. So another method we astrophotographers use to reduce noise is what we call stacking. This again is a technical word. I'm introducing these technical words for the benefit of those who probably may be hearing for the first time, or maybe you have heard of it, but you don't know what application it has. How do you use? What benefit do you have if you stack your photos? So I received several questions, some very interesting questions, asking, I just have a simple camera. I don't have these dedicated big astrophotography cameras. I'm using my phone. Okay, I'm using a simple DSLR. Can I achieve good astrophotographs? Yes, you can. You can to a certain extent by using stacking. So what stacking does, instead of taking one photograph, okay, we astrophotographers, we take multiple photographs of exactly the same location of the sky. So I don't move my camera, I don't move my phone or my DSLR. I point to the same location and rapidly I take multiple photographs, one after the other. And on the computer later in post-processing, I combine them. Okay, this is the process of stacking. So what happens is, if you recollect my earlier slide, I had the signal, which is the light coming from the distant stars and the galaxies and the nebula. And I have the random noise which is generated by the camera. So if I stack multiple photos, the signal goes up, whereas the noise remains where it is. So I'm able to extract the noise from the signal. So on this particular slide, the image on the right hand side is a single image. It's a
I didn't
single
understand
row.
about stacking. Can you please repeat?
So stacking is a process by which you take multiple photos of the same object. You take multiple photos and ideally in what we call a raw format. Okay, so in camera, you can capture raw format or JPEG format. So JPEG format is probably people are more familiar with, but a camera captures in raw format. The raw format captures more data. Okay, but I encourage you not to just capture in raw format, but take multiple images in raw format. So for instance, you, instead of taking one photo of the Orion Nebula or one photo of the Milky Way or even the constellations, you take quick, let's say 10 photos, okay, or 20 photos, however you can quickly. Okay, I will talk about how you can take them quickly also. But once you've done that, you have 10 images. Now you combine all those 10 images in the very software available. I'll mention the software. And the software do a very good job of combining these multiple images and producing one single image. Now that one single image will be of high quality. If you can see on the screen, the image on your right hand side is a single image, whereas the image on your left hand side is a combined stacked image. If you can see, the noise has drastically reduced. So this is the magic of stacking. This is what stacking does. You can combine multiple images, multiple raw noisy images, even if they're noisy. When you combine them and when you stack them, you can reduce the noise and you can increase the signal. Once that happens, then you can then extract more information. You can extract color, you can extract details. things that you did not even know were there in your raw data. Okay, so how exactly stacking is done is a big sort of, it requires maybe another session, but I want to introduce this topic called stacking. So maybe you can go back and do a little bit of homework, but before I can actually give you the name of these stacking software.
Sir,
Okay, so
sir, can you please again explain noise?
noise.
Yes, sir.
All right, so can you see these two images in my slide?
Yes, sir.
The slides is stacking. Okay. Now on the right hand side, in fact there are two images of the same thing, which is a wide angle photo of the Orion Nebula. Now on the right hand side, can you compare how the quality of the image looks? If you see closely, you'll see graininess in the image. So where it's supposed to be black space, you'll see something grainy. Can you make out something graininess? It looks as if it's an old film kind of image. On the left hand side, that graininess is less. Okay. I hope besides the color difference, now if you look at the right hand side image, you'll also see it has a different tint. It looks brownish. It looks brownish, and if you look closely, you'll see that it's not a clean image. It doesn't look clean. It looks as if sand has fallen on it, or there's a dust fallen on it. So this essentially is how noise looks like. Now, why does it happen? So we are using electronic sensors to capture data. The data being the light from the heavenly stars. So electronics has a tendency. Electronics essentially works on microcurrents, and these microcurrents, essentially, they are basically small signals. Now, I'll probably need to get into a little bit more in depth to explain exactly why noise happens. But to put it very sort of simplistically, um, it's a random signal, okay, that is never zero. There's always a bit of electronic signal, okay, in an electronic circuit. The electronic, because the camera is essentially basically an electronic circuit. So in that electronic circuit, you are getting a lot of this signal, which is because the camera is producing that signal. It is not actually real signal. So when you see a color there on the camera sensor, okay, the color has not come from the Orion Nebula. The color is because the camera has produced that color internally. We don't want that. Okay, so that's what noise is. It's an internal electronic signal being produced by the camera. And as I've explained, if the heat, it increases with heat, generally speaking. So if you can reduce the heat, it will be less. So shooting from a colder place can also reduce noise, but there are more sophisticated ways of reducing noise also. And the best way is stacking. So if you take multiple images and you stack them, finally you get a picture on the left, okay, which is a cleaner image, which you can then post-process. All right. I hope that's sort of answered. If there are more questions, we'll probably take them at the end of the session, okay, because it's a deep topic. I understand it's a deep topic about stacking and noise.
Hello.
Yeah.
So I think so. I've searched about the deep sky stacker, and
Okay.
it is a image. And in that image there are various numbers, 600.0 means how the means what will be the range of the um, photo of means what will be the warmthness of the photo, and there are filters and all, means it will be a deep topic. So how can we learn that, means how to
Yeah,
stack.
I get it. I completely understand sort of the question and sort of the concern. Some of these software, they require a bit of learning curve, as we call them. Okay, they require someone probably to guide you initially, to explain to you what each feature means, because it can get a little bit confusing, and some of them are not very easy to learn also. Unfortunately, I think since what we started, so the plan was we'll start this discussion, And then subsequently, if there's interest, okay, now that you express an interest, maybe we can ask the administrators to arrange one more session where maybe I can talk about processing images in Deep Sky Stacker. Okay, then I can get into specific menus, what formats to use, when does Deep Sky Stacker fail, can you use this setting, that setting, are there any alternatives? So yes, yeah, I understand you'll have more questions, or you can always mail me. My mail address is available. I can try to understand your question. Maybe you can answer this offline also after the meeting also.
Okay, so thanks.
Sir, I have
Okay.
a question. Sir, what are the best telescopes we can buy? I am a student. So what are the best telescopes?
Okay. So yeah, this is a very common question. Which is the best telescope? I want to buy the best telescope. So it it depends entirely on what you want to see. Okay. So if you want to see planets, I can tell you a different kind of telescope. If you want to see a deep sky nebula, then there's a different telescope. For astrophotography, there's a completely different telescope. Okay. So what we'll do today is that I'll take you through this flow and we'll talk about telescopes that are good for astrophotography. Uh, Unfortunately, there's no one best telescope. So the same telescope that you use for visual to see planets may not be the best telescope if you want to take a photo of the Orion Nebula.
Sir,
Okay.
I want to see the stars. Stars.
Okay. All right. So yeah, I mean, if it's a sim, if you just want to see the stars and you want to see the planets, the easiest probably would be a reflector. Let's say anything between 4" to 8", a Newtonian reflector with an alt-azimuth mount. Okay, that's what I told you. Just a design.
Can you repeat the telescope name?
Sorry, the name. So what I'm telling you is actually the design of the telescope. So there are a couple of designs. So the simplest is a Newtonian reflector. So the Newtonian reflector is what I would recommend for anyone who's beginning. Newtonian reflector. The size of the mirror, the Newtonian reflector has a mirror. At the very least, I would suggest a 4". If you can manage an 8", but if you're just a beginner, if you don't have a parent to help you, 8" might be a little bit difficult. So I would say at least a 4", and a good solid tripod. Okay, the tripod is something that holds the telescope in its place. Okay. Again, drop me a mail. I think because since we started about astrophotography, we'll continue this topic. But send me a mail, or we can connect after the lecture. We can talk more about specific details or specific brands or where to buy the telescope. Because I just gave you a design. I didn't tell you anything else. Yeah, but we'll talk about it a little bit in depth also. Sorry, I'm sort of skipping ahead because there's lots to cover on the astrophotography topics itself, but we'll cover. We'll make sure that you can get a good telescope. So what I've listed here is some software which I personally use, and I found them useful for stacking multiple multiple images. And again, it depends on what kind of image you're trying to stack. For deep sky, it's Deep Sky Striker, as the name says. For planetary, there's another software called Registax, because deep sky requires a lot of stars. A planetary photo will not have stars, so Registax takes care of that. And Sequator is something that is useful if you like to shoot astro landscape. So what's astro landscape? We'll see. We'll see in this coming slides. Okay, so a very important concept here, because as you probably see, I'm trying to sort of make certain basic fundamentals sort of clear. So there's a concept called, or the two concepts. One is the field of view and focal length. If you already have a telescope, you'll be familiar with these terms. But if you're not, no worries. So if you use a telescope or a camera lens, okay, you will realize that there is a number there, which is called a focal length. Okay, so if you use a wide angle lens, okay, so this, for example, is a 8mm lens. It will give you a field of view which is 180 degrees, which is if you're standing, you will see more than what your eye can see. Okay, horizon to horizon. Okay, that's 180 degrees. That's a wide, extremely wide view. Of course, it will be a distorted view because things will not look straight. Okay, at the corners you'll find them curving. Okay, this is so this kind of view is called a fish. This kind of lens is called a fisheye lens. So if I go a little bit closer, I have an 18 millimeter focal length. This will give me about 100 degrees view. So it will cover a slightly less portion of the sky, okay, but still quite wide enough. So people who are interested to shoot something like the Milky Way, okay, or wide regions of the sky, okay, they would use a camera lens which will be according to this this focal length. Then if I go even closer, then I can use a 50 millimeter lens, and it will give me a 70 degrees view. So even shorter. Okay. If I go with a 300 millimeter focal length, okay, the field of view drops even lesser. So what you realize is that longer the focal view, shorter is the field of view. Similarly, longer the focal view, greater is the magnification. So you can't use one single focal length to capture every object in the sky. Okay, so if your telescope, okay, is, let's say, 1000 millimeter focal length, okay, as here, it will give you a close-up of the moon. But if your telescope is, let's say, 50 millimeters, okay, 50 millimeters focal length, obviously your moon will look small. It will not look as large. In the field of view will be large. You'll see a large portion of the sky, but objects like the moon or the planets, it will look tiny. Okay, I want to explain this a little bit in more in depth, because this is very important. This makes this, with this you can decide what type of equipment you can buy. So if you are interested to photograph planets, you necessarily need to have a telescope which has a focal length which is more than 1000 millimeters. Okay, if you have a telescope which is, let's say, 500 millimeters or 300, yes, you can get the planet, but the planet will look tiny. Why? Because the solar system objects they look small. When you look at the rest of the sky, they look small. Okay, so some people may find this surprising, because solar system objects are the planets and the moon, they are relatively close to the Earth. On the other hand, distant nebulas, okay, like the Orion Nebula or even the Andromeda Galaxy, they actually appear large in the sky. So Andromeda, okay, if we can see the entire breadth of Andromeda, would actually be more than 6 diameters of the full moon. So Andromeda is actually quite large in the sky. It's just that it is so far away, it is faint, so you don't see it. But if you were to take a photo, okay, you don't need a very high focal length to capture deep sky, some deep sky objects like nebulas or Andromeda, especially if they are large in the sky. So it is very important to understand how big the object looks in the sky. Okay, we call this angular distance or angular, angle that the object makes in the sky. So depending on how large the object looks in the sky, you have to choose your focal length. Okay. And that brings us to the next topic, which a lot of people are asking as to what gear do I require for astrophotography? Do I necessarily need to have a telescope? Do I necessarily need to have a big camera? Do I need to have dedicated astrophotography camera? So yeah, so no, you can start astrophotography even with simple equipment. Okay, but we'll talk about both simple and we'll talk about the more advanced equipment also. So again, this question has come up multiple times as to which camera is the best. So I would say the camera that you currently have with you probably is the best camera for you, for you to begin astrophotography, because you can, the only way to learn astrophotography is to try it. Okay, is to go out and try to take photos. When you try to take photos, you learn something. Then you read up. Okay, you ask questions to people like me or anybody else. You learn and you take more photos. Only when you realize, okay, what limitations your camera has, okay, or what appeals to you, okay, then you can decide whether you want to go for higher cameras or you're happy with your existing camera. Okay, so it's entirely up to you, and you can do quite substantial astrophotography even with modest equipment, even with a smartphone, for example. Okay, you can do quite nice astrophotography. So we'll see what each of these can do, just for the sake of explanation. So what I have here, the first one is a smartphone. So it can be, I'll just put some brand name. In any smartphone nowadays is, most smartphones nowadays are quite good enough to take photos. Now, there are some limitations. The limitations being that obviously you cannot change the lens on a smartphone, which is required, which mostly the DSLRs or the dedicated astrophotography cameras let you do. Also, they are limited in low light conditions, because astrophotography obviously requires that you take photos in low light conditions. So the sensor is not sensitive enough to capture low light conditions. But again, that's changing. Okay, so some of the modern cameras, more modern smartphones like Google Pixel 4, for example, actually has a dedicated astrophotography mode. What it does, it takes multiple photos and stacks them and gives it to you. So you don't need to do the stacking part yourself manually. You need to only have the smartphone and something like a tripod. The tripod will hold your smartphone in place, and it can automate the stacking process also. So the Google Pixel 4 does that. iPhone, I've seen some people take very good photos with iPhone also, and Samsung Galaxy or any Android phone for that matter is pretty sort of similar. Okay, and then we look at where you can use these smartphones. DSLR generally are quite versatile. Okay, so by that I mean you can use it not just for astrophotography, but for everyday photography also. So that's the reason many people may already have a DSLR. And the best thing about a DSLR is that it gives you complete control over most aspects of photography. So when I talk about photography, we'll talk about the specific controls of exposure, the shutter speed, aperture, and ISO. Okay, so what are these? These sound very technical, but we'll see what these are. So the DSLR gives you control over that. And the best cameras, the high-end astrophotography cameras, what they do is they in fact don't have something like a screen where you can see the resultant image, but their sensors are extremely sensitive to low light. Secondly, I mentioned about something called readout noise. When a camera is reading deep sky image signal, there's an error which is called the readout noise. That readout noise is extremely low in dedicated astrophotography cameras. Also, some of these are cooled internally. So the temperature of the camera is cooled. So the noise, the thermal noise does not build up. Okay. Apart from that, so some of these cameras are extremely sensitive to certain wavelengths, which is emitted by emission nebula. So you can have a hydrogen alpha filter, so which will capture your deep sky red nebula. Okay, most of these emission nebulas are emitting a hydrogen alpha wavelength. So you'll find that these are most sensitive to a particular wavelength, and that gets you more color, more detail in dedicated astrophotography cameras.
So,
yeah.
If we don't have a tripod, then can we use a selfie stick?
You can, yeah, you can do that as long as the selfie stick is pretty stable. Okay, so what do I mean by stable? So when you take a photo, a long exposure photo, typically when you take a selfie, you take click, it's a split second. Astrophotographs typically happen in multiple seconds, maybe 5 seconds, 10 seconds, 20 seconds. So for that duration, you don't want the camera to shake at all. Okay, so if you keep your selfie stick on the ground, okay, you don't want anybody to shake it. Okay, even if you pass close by, even your walking by will shake a long exposure photo. So any tripod or any stick is fine as long as you can keep it steady for the duration of that photo. So this is something again we need to get used to, because when you take normal photos, okay, daylight photo, and most of them are automatically taken by the camera. When you hear that sound click, so there are actually two sound, click and click. So it happens in a split second because it's taken in daylight. Now, if I take the same photo during night, it will be click, and the next click will be after 30 seconds. So between the first click and the second click, the camera shouldn't move at all. The camera can be a DSLR, it can be a smartphone, it can be on a tripod, it can be on I don't personally don't use a selfie stick, so I'm not sure of the stability of the selfie stick, but you cannot hand hold it. Okay, so you need to keep it on the ground, and nobody should be touching it. In fact, you should not even touch the screen to start the exposure. Okay, if you start it, there should be a delay when you touch it and when the camera takes the photo, because even the fact that you touch it, even that little bit of shake is enough to spoil your exposure. That's how sensitive it becomes when you take longer exposure photos. So yeah, anything is fine as long as you have to keep it steady. It should be extremely steady.
Can we use a chemical tripod, that stand you get for the burner in chemistry?
Yeah, I think I know what you mean. My daughter has the same thing. Yes, I think that should work. Yeah, as long as you keep it at a distance, that should work. Yeah, I think. Yeah.
Can we make a tripod at home?
You can. You should be able to make a tripod at home as well. And even if you have a simple tripod, you can always make a tripod a little bit more sturdy by doing things like attaching little weights to it. That little weight could be, you attach a polythene bag at the side, and you put something in the polythene bag that makes it heavier. Ideally, it should be as heavy as possible. Okay? Generally, if you notice telescope tripods, they're pretty heavy. Like if you see a telescope tripod, they don't move very easily. They're quite heavy. All right. So I think what we can do, I'm sure there are a lot of questions, and I can see that coming. So perhaps we can complete this presentation, okay? Because there's lots more I want to sort of cover, and I'm sure at the end of it, some of your questions might get answered, and maybe you'll have more questions at the end of it. Okay. So and I think we're coming close to an end. So let me proceed. Okay. So there's lots more I wish to cover. So. All right, so an ideal camera, it doesn't matter whether it's a smartphone or it's a DSLR or it's a dedicated astrophotography camera. It should let you control these three factors. Okay, there's a shutter speed, aperture, and ISO. Okay, so these control how much light is coming in. So this probably will give you an idea. This is what we call aperture. Aperture is how wide the camera opens. Okay, so the more it opens, the more light comes in. So this is what we call the aperture of the camera. Shutter speed, I have here two photos. Okay, it's a wide angle of the Orion constellation. So this is taken at 30 seconds exposure. So as I mentioned, when it click and then the next click happens after 30 seconds. And I have this much of data. Okay, this much of information is captured. Now look at 120 seconds. You'll see a lot more information is captured because this is 120 seconds. So the bottom line is that if you can increase the shutter speed, okay, you'll get more light. More light means more information, and then you'll get more details, more color in your astrophoto. Okay, so we talked about different technicalities, but what type of astrophotography can you do? So I like to break them up into these three categories: astro landscapes, deep sky, and solar because they require different equipment. So the equipment required for astro landscapes is, yes, you require something like a smartphone or a DSLR, which you need to attach to a tripod. You require something called as a fast and a wide lens. Okay, fast, so that the aperture is wide. We talked about aperture just a couple of slides back. So if you have wider aperture, it will get you more light. Okay, and wide lenses, it looks at a wide part of the sky. So the field of view is large. Okay, and then tripod, as I mentioned, it has to be some kind of stand, a tripod, and hold the camera in place. Intervalometer is this device that you see here, that so this is the device called intervalometer. So this lets you program the camera so it takes photos automatically. Okay, so you don't need to press the button. Okay. If you don't have an intervalometer, you should at least have a remote trigger. So you do not physically start the camera. Okay. The remote trigger can be a physical device, or it can be something in the camera itself. So you can have something like a delay. So you click on the camera and it starts after 2 or 5 seconds. So this is what we call automating that data capture process. So as I mentioned, it can be an external device like an intervalometer, which is plugged into the camera, and you can program it to take photos continuously, one after the other. So you don't need to press the buttons. Similarly, your camera internally may have an intervalometer. Okay, some of the Nikon DSLR have this feature. They have an inbuilt intervalometer. So you can program the camera to start at a certain time and keep on shooting automatically without you needing to do anything. You can go, in fact, and sleep, and then the camera will be taking photos automatically. And the same thing can be done by connecting your camera to the computer. So there are software that can do the same process on the computer. Okay, so the lenses that are used in astrophotography, especially astro landscape photography, have these characteristics. So there are wide. So when I say wide, that means the field of view is wide because you're covering a large portion of the landscape. They are fast. So F ratio or the aperture is wide, is big. So more light can come in because you're shooting at night. So you need more light. And they are what we call prime lenses. So if you have a DSLR, okay, and you have a kit lens, you'll realize that you can zoom in and zoom out. Okay, in a prime lens, you cannot do that. The focal length is fixed. So you cannot zoom in and zoom out, it remains fixed. But because of that, there are less optical errors produced by the prime lenses. So think of it as a sort of think of a telescope as essentially a prime lens. The focal length of telescope doesn't change. It remains constant because it is made for having best optical performance. Okay, so it's not so much of zooming in, zooming out, but good optical performance. Similarly, there's some camera lenses which are prime lenses which can give you the best performance. Now, what is possible with the entry DSLR? Again, this question came up a number of times. So I'm actually sharing an image I took. This is probably my first photo of the Milky Way, taken about 10 years back. This is taken from the Himalayas. And it's taken with a pretty entry-level DSLR, the Nikon D5000. And I use the kit lens. So most people, if they're buying or they already have a DSLR, they'll probably have a similar kind of camera. And this is 10 years back. Entry-level DSLRs now are much more advanced. They have better sensors. So these are some of the data, or the EXIF data, as we call them, which I've mentioned here, so that for easy reference. Now it doesn't mean that if you replicate exactly these settings, you'll get exactly the same result, because it also depends upon, and more importantly, from which location are you shooting. So location is very important. So luckily I was in a very dark location where I could see the Milky Way very clearly. This is a place called Ranikhet at Uttarakhand. So it was very dark location. had been there for astrophotography dedicated trip actually. So it is pristine dark skies. Yeah, but this is something that's possible even with a pretty basic DSLR. You can do this kind of photography. This is what we call an astro landscape. You have an astro object and you have a landscape. You can take photos like this. This was a lunar eclipse, 2011, again taken with the same camera, but with not with a wide angle lens this time, but with a 7300 millimeter lens. So it's a more of a zoom lens, which was required because at that time I didn't have a prime lens and a fixed tripod. So the building here is the Burj Khalifa. If you recognize it, the tallest building. I used to live in Dubai in those days. So there's a nice red eclipse. Yeah. So this is pretty much what you can do. This is you can of course capture the International Space Station. So the International Space Station flies pretty regularly, and I think people of the astronomy group are aware. I think some of you have taken photos of the International Space Station as well. So you can plan to the second when the ISS would be seen in your part of the city or your part of the town. And you can even ask the system to the app to send you an alert. So whenever the ISS is going to pass by, you can go out and watch it or even take a photo. So this is again a wide angle photo. So ISS looks like a star which is passing, which is moving. It doesn't blink. It looks pretty much like any other satellite. Okay. So the reason I'm getting dashes here is because it was moving quite quickly. Okay, it moves quite quickly actually. If you need a close-up of the International Space Station, then you need to shoot it with a longer focal length. So this was just 12 millimeter. So ideally you would require something like 1000 millimeter if you want to actually see a zoom up view of the International Space. And some of my friends have done it. So what you need to do is you first decide where it's going to pass by, point your telescope in that location and take a video, because it's so quickly that you cannot take a photo. You keep on taking a video until it passes in your field of view. And then later on, from the video, you extract that image. That's how International Space Station is generally shot. So this was taken in the desert with a slightly better equipment. So I had then upgraded to a Nikon D7000, a slightly better DSLR with a fast wide angle lens. It is no longer a kit lens. But again, this is a fixed tripod. This is taken from the desert in Abu Dhabi. Meteor showers can be captured by similar equipment. Now, again, meteor shower, you do not know when a meteor is going to streak by. So what you do is you set up your camera on a tripod and keep it on auto mode. You use an intervalometer to continuously take photos throughout the night. In fact, I use multiple cameras pointing in different directions. And then throughout the night, you'll find that the camera has captured a lot of these meteors. This is not a single image. So this is an image which is taken, it's a result of multiple images taken over the entire night and then combined using Photoshop. Okay, so when we do something like this, I have to make sure that I rotate the position of the sky to accurately reflect where the direction of the meteors are coming from. It's again something that probably needs to be shown rather than talked about. Maybe we can have a detailed workshop a little bit later to explain how this is done. This is another meteor shower. This was Gemini 2017. So this was not on a fixed tripod. This was on a tracking mount. So in a tracking mount, the camera is being tracked through the sky. So I do not need to rotate the sky in post-processing. Okay, it's the camera is looking at a particular fixed location in the sky. And as and when the meteor shoot by, it gets recorded. But again, these are not one images, it's multiple images. So star trails. I think you probably would have seen a lot of these images like these, which call star trails. So since the Earth rotates, it moves. If you take photos, long exposure photos of the stars, they'll seem to move across the sky. And depending on which direction you point, so I'm pointing my camera here towards the north celestial pole, and the star at this near the center, this is Polaris. So Polaris doesn't seem to move, or it moves very slightly, and all the stars seem to move around Polaris because this is the north celestial pole. So this was taken about 4 hours, about 400 images combined in post-processing in a software called Star Trails. Similarly, this is a Star Trails photo, but you'll notice something different here. There is no central star. That's because this was taken from Australia. And Australia is in the southern hemisphere. And in the southern hemisphere, we do not have a bright star near the south pole, near the south celestial pole. So there's nothing here. But yes, the south celestial pole, every star seems to rotate around that south celestial pole. It's just that we don't have a bright star there. Okay, so this was taken from South Australia. This is, again, astro landscapes can be used to take photos of the Milky Way, wide angle photos of the Milky Way. So this is taken from the desert, from Abu Dhabi, and it's again not a single image, it's a stacked image. So stacking drastically improves the quality of the image. So this is 16 images stacked together in a software called Sequator. So, okay, so we talked about a fixed tripod, right? And then, but there are some limitations of using a fixed tripod. And what are the limitations? The limitation is that our tripod and a camera is on Earth, which is not fixed, it is actually moving. So when you take photos of the night sky, this is what you'll find. You'll find the stars trailing. You saw some of those in the star trails, which look nice. But what if you don't want star trails? You want to take image, want to take a photo of a deep sky object, okay? And you want the stars to look like stars. You want the stars to look like pinpoints. For that reason, there are two things you can do. One is that you limit your long exposure. Okay, so in fact, as it turns out, there is a formula, there's a rule, which we call the rule of 500. In fact, now I should probably call it the rule of 400, because cameras now are better. They are better, have better resolution. So the rule of 500 no longer applied. It should probably be the rule of 400. But anyhow, the concept is this: is that you take the rule of the number 500 and you divide by the focal length of the lens that you're using. So if you're using a focal length of, let's say, 50 millimeters, so 500 by 50, 10. So 10 seconds is the maximum exposure you can give to your long exposure, beyond which the stars will start to trail. Till that limit, it will trail, but it will not be discernible. It will not be easily visible to the human eye. Okay, only when you zoom in, then you'll find, oh, it's not a perfect dot. It is slightly trailing. Okay, so it's okay if you're using to take photos just for artistic purpose. It's okay, a bit of trailing. But if you don't want this, if you want to take photos of pinpoint stars, then you need to have something called tracking. And tracking is achieved. So the traditional way, or the classical way, or the popular way, is what is achieved by a telescope mount called the equatorial mount. So this equatorial mount tracks the motion of the stars. It compensates for the Earth's rotation, and it will keep your object in the field of view constantly. Okay, so I'll not go into how it does it, because again, that requires pretty sort of detailed technical discussion. But an equatorial mount, okay, with one axis pointing towards the polar axis, the other axis will track your stars through the sky. So you'll not get star trails. Okay, you'll get a long exposure photo. You can go not for 30 seconds or 20 seconds, you can go for minutes, sometimes more than that. So again, within tracking mounts, you can have the equatorial mount, which is on the left hand side. This is quite a heavy duty. In fact, this is my mount. I have this particular mount, but I also have the mount here on the right. which is a smaller version of a tracking mount. So why these two versions? So the difference is in the payload capacity, how much weight it can carry. So the big one, it can carry up to something like 20 kilos of weight, of telescope weight. So I can have a big telescope attached here and can track that so the sky accurately. This one, it's about maybe 4 kilos. So I can have a DSLR with a lens. So if I don't have a telescope and I still want to track and take deep sky objects, it's possible using these portable tracking mounts. These things were not available even 5 years before. Okay, they're more or less recent development, and they're getting better and better. So if you only have a DSLR, okay, and you want to take deep sky images, you actually need not actually get this big amount, because this heavy, it is expensive, it's cumbersome to carry around. This is quite portable. So if you want to get introduced to astrophotography, deep sky astrophotography, you can start with something like a tracking mount as well. Okay. Of course, there are pros and cons and limitations of this, of both. So with smaller mounts, you can have smaller telescopes. Okay, so there are some small, so this is opposed to what I would advise to someone who is a purely visual astronomer. So someone who wants to look at planets, who wants to look at deep sky objects, wants to look at it. Okay, I would advise get an 8-inch telescope, get a 10-inch telescope. So when I mean 10-inch or 8-inch, I mean the diameter of the telescope. Here, for someone who's looking to photograph deep sky objects, I would recommend these refractors, okay, which are smaller. So this one is only 2 inches. This is 3 inches or less. This is my telescope. This is 4 inches, more than enough to capture a majority of the deep sky objects. That's because in deep sky objects, the objective of these telescopes is not so much to gather a lot of light in one go. Okay? It is more to make sure that the optics do not produce any aberrations. So typical optics like camera lenses, okay, they produce a lot of aberrations. So what I mean by aberrations, the stars will not look like pinpoint stars. They look like commas. They look like comets. At the side of the image, they will start to make sort of comma-like shape, or they start to drift. The field will not look flat. Okay, they look circular at the edge. All these are optical issues. These telescopes, they have correcting mechanism to not, so that your final image doesn't have these issues. So even though they look small, they are best suited for astrophotography. So that's the reason. It depends a lot whether your interest is in astrophotography or visual, okay? Because the telescope optical tubes specification is slightly different. Okay, so there's a question asked, so I just want to use these two images to show that. So how do I get high resolution photos of the sky? So this is a photo of the Andromeda, which was taken with 180 millimeter lens. And it was tracked by a portable mount. So this portable mount is the smaller camera mount, and the focal length was 180 millimeter. As you can see, it's nice, and you can see sort of good detail. But if I want more details, then I'll need a larger focal length. And since the focal length is more, the weight of the telescope is more, the simple tracking mount will not do. I'll need to use a heavy mount. So this is a higher resolution image of the same Andromeda. And you can see the focal length is more. It's 550 millimeters. So with more focal length comes more magnification and more resolution. As you can see, it is more sharper. The image is more sharper. Of course, you can't do that with smaller mounts. This is where you need heavy duty mounts like the EQ6, the Equatorial Mount 6 Pro mount, which is quite popular. Okay, so using some of the portable tracking mounts, I've taken these images. So this is a wide angle photo of the Milky Way. I'll go through these because there are lots, and then we'll come to some discussions later. So you can make a note of it. If you have any questions, we can talk about how these were taken. So this is again a wide angle of the Cygnus portion of the Milky Way, again taken with a portable star tracker. This is taken with equatorial EQ6 mount with a Nikon camera. 810A, the A stands for astrophotography. It is a little bit more sensitive to the hydrogen alpha wavelength, which is that's the reason you see a lot of these red color in the photo. And this is of course the Orion Nebula. Okay, so then we come to the sort of the topic of solar system astrophotography, where you have capture images of the moon, the planets, the sun. Now, as I mentioned, these objects, even though they're closer, they are smaller in the sky. They look smaller in the sky. The apparent size is smaller. So they require a longer focal length. Essentially, it means you require a telescope. Okay, so here we can't have simple camera lenses. We need to have a telescope. And the way to attach your camera or your smartphone, there are two methods. One I call a afocal method, which is you attach your camera or your smartphone directly on your eyepiece. So if you're used to a telescope and you're already watching Jupiter or Saturn nowadays, which are in the sky, you can simply use something like this simple adapter, keep your smartphone there, and you can take photos. So this is where smartphones actually excel. Okay, you have these nice adapters which come and which are quite handy, and you can take these afocal method photos. On the other hand, you can attach a DSLR directly to the camera by removing the eyepiece. So here, I've actually removed the eyepiece and attached the DSLR body directly to the telescope. The telescope essentially becomes the lens for the camera. These are some of the adapters which I find useful. For the camera, they're called T-ring adapters. And there are various adapters. This one is, I use this one for attaching my smartphone. This one I think it's by Celestron, but there are many others. So with this, you can capture good, nice photos of the moon. This was taken with my 8-inch with Cassegrain. The focal length of that telescope is 2000 millimeters. I actually had to reduce it so that I get the entire globe of the moon. You can of course produce something like this, which is a mineral map of the moon. So if you take multiple photos, you stack the photos, and you can actually extract more information, which is the color information. The moon's surface actually has subtle colors, which is a reflection of what kind of minerals are there on the moon. There's a lot of titanium and basalt. So you see that in the color that you can extract these colors by taking these high resolution photos. And of course, you can take photos of the sun as well. Of course, you should never look at the sun or take photos of the sun without using proper protection. So here I'm using a solar filter, which cuts off 99.99 actually % of the solar radiation. So these were two rare events. Mercury transit 2016. There's another transit that happened 2019 as well, but it wasn't visible from my place. And even more rare is the Venus transit of 2012. The earlier transit happened 2004. So Venus transit happens after a gap of 120 years, and then it occurs after 8 years, and then again it will happen after another 120 years. An extremely rare event. So yeah, so this event actually was quite significant in the olden days when it was used to calculate the distance between the sun and the earth, the one astronomical unit. There's a nice question somebody asked about using parallax in astrophotography. So this, you can think of this as one example. So parallax is you observe a particular object, let's say a distant object, from two different locations. And since the distant locations are separated from, you'll find that it looks, the same object appears to be in a different position in the sky. And by noting exactly how different it looks from two different locations, and by knowing the distance between these two locations, you can actually calculate the distance to that particular object. So this was roughly the mechanism being used to calculate the distance between the Earth and the Sun, the one astronomical unit, during Venus transits. Multiple people used to time the Venus transit, and they used to compare that, and then essentially using trigonometry, you can calculate the distance between the Earth and the Sun. So this was very historical event used in the past. So planetary photography requires extreme lot of magnification. It also is the one that requires a lot of cooperation from the atmosphere. So generally what we do is that we don't take single images of planets, we take videos. The reason is because at higher magnification, the turbulence of the air becomes significant. So you, at 1 second, you'll see the great red spot on Jupiter, and next second it will be gone. If you're used to looking at it through an eyepiece, you realize what I'm talking about. So I cannot take, I cannot time my shutter. Okay, I don't know when to click. So rather than guessing that, what people do is we take a video of Jupiter, okay, or Saturn, or Mercury, or any in the planet, and using special software, the software can look into that video, extract the images, and then stack the images to produce a single high resolution image. So this actually was a video of Jupiter, a 2-minute video, okay, which I processed in raised stacks, and then finally we get a final processed image. All right, so I think we covered a lot of things, and I realized I think we sort of overran the time a bit. So are there any further questions and answers? I'd like to sort of open up, and yes. Yeah.
Sir, I have a question. Sir? Sir, excuse me. Sir? Sir? Yes, sir. Can you repeat the name of telescope you suggested me to buy?
Sorry, you want me to repeat which telescope is that?
Name of the telescope which you suggested to buy for students. Means spelling.
The telescope that I suggested to buy for
Students.
I'm sorry, I didn't quite get that. Can you repeat that again, please?
Sir, can you repeat the name of the telescope you suggested to buy for students?
Hello.
All right. So I think I suggested that for visual only. Okay, so for visual, a Newtonian reflector. So it's not a name; it's actually more of a design. So you can buy a Newtonian reflector with a brand like Skywatcher, okay, for example, or Vixen, or anyway. So a Newtonian reflector essentially is the design of the tube. And then there are two things you need to consider. One is the optical tube, and one is the mount. So the optical tube I would recommend for beginners is a good one is a Newtonian reflector, at least a 4-inch reflector. If you can, buy an 8-inch one. And then the mount, if you're not going to do astrophotography, I would recommend an alt-azimuth mount. An alt-azimuth mount with a Newtonian reflector. There are many variations of this. So a Dobsonian can be one of the designs. Again, it's a variation of the Newtonian on an alt-azimuth mount. So yeah, that's only the design of the telescope. If you want to have a specific brand, I think we'll connect a little bit offline, and I can give. Yeah.
Sir, can I ask you 3 questions?
All right, go ahead.
Does the universe revolve?
Yeah, that's a deep question. So if you say okay, so it's a probably not relevant to the topic that we're discussing, and I would probably say that nobody knows the answer to that, because if you say it revolves, the question would be what would it revolve in reference to, because you need some reference for movement. So what we've seen so far as the universe is concerned is nothing is in motion. Nothing is stationary. So everything is in motion. Okay, but we haven't found a proper revolutionary motion for the entire universe. So everything seems to be moving apart on a cosmic scale. So if you look at the galactic scale, the galaxies seem to be moving apart away from each other. Okay, so now whether there is some proper motion for the entire universe, I'm not sure. I don't think so. Uh, if I understand sort of the current understanding of the Big Bang and the acceleration that is happening, um I'm not sure if there's a proper revolution motion. Yeah, but again, I'm not probably a cosmologist or a scientist to be 100% sure on that. Okay, but my understanding, as my understanding goes, I don't think there's a proper revolution motion detected.
Hello, Amol. Hello. क्या कर रहे हो पिक्चर जैसे अभी यूट्यूब को कैसे समझाना है ये क्या है ये क्या है ऐसे पिक्चर देख के समझिएगा ना ऐसे तो समझ नहीं आएगा
All right. So yeah, it's a very fascinating question. I think just that there is probably we'll probably have to take it up as is another session on cosmology, I guess. Are there any specific questions on astrophotography or the topics that we covered or the concepts that we covered?
Hello. Hello.
Yes, yes, please go ahead.
Sir, I have a question that can we take the photos of the sun during daytime?
So
So how we can see the means movement of the gases or something?
yeah, so yes, of course you can. So it requires adequate protection. So it would require a solar filter. So again, there are kinds of solar filters. There are solar filters that will give you a neutral um, color of the sun, so it will look whitish. It will look sort of slightly sort of yellowish. There are other dedicated telescopes which will give you not just a neutral view, but actually it will give you a very clear picture of the solar surface. Okay, so it's sensitive to the wavelength in which the sun is emitting. So hydrogen alpha is one of, because the sun is mostly made up of hydrogen, right? So there are certain, so you can go two ways. Okay, you can, if you have a regular telescope, all you need to do is buy a solar filter that you affix to the front of your objective. Okay, so the light coming is um, is constrained, is restricted, so that only a minimum part of light is brought in, and you can view that as you normally would in any other object. So the solar light is reduced. And the other option is that you have a dedicated solar telescope. Okay, so there are some dedicated solar telescopes that have special glasses which which allow only uh, wavelengths that lets you actually observe what's happening, things like solar prominences, okay, or magnetic storms happening on the sun. You can actually see some of them in real time. Probably that's the only activity in the entire sort of astronomy universe that you can observe in real time. Activities on uh, our own star.
Hello.
So yeah, so, but be careful if you outside. These are special filters, and this is a special telescopes dedicated only for solar. So I would suggest don't try to make your own filter. Buy it from a reputed brand. Yes, because as you know, safety is paramount when it comes to looking at the sun.
So, how to photograph the International Space Station?
So in my sort of slide, I talked about one way of photographing it. So there are two ways. Okay, so one is that you photograph it the way it looks, which is it looks like, if you see in the International Space Station, it looks like a star. It looks like a star, but unblinking, and it's moving at a rapid pace. So it looks like any other satellite. So if you notice satellites during after sunset or before dawn, they look like a pinpoint of light crossing the sky. Okay, so and you can take a wide angle photo. You can even use a smartphone, and you can capture that. It's pretty easy. Okay, so you can have a smartphone. You can simply take a photo, and it will generally come out all right. Now, the second option is more difficult. If you want to have a clear view of that internal space, so that it doesn't look like a pinpoint of light, but actually you can make out the solar panels and the modules and all that, then you require a larger focal length. You essentially require a telescope. Now, the trick is that you cannot move your telescope quickly enough, because the telescope is, the internal space is zooming across the sky. So planning is very critical here. You should know in which direction it's going to pass, point your telescope there, okay, and keep on taking video until it passes the field of view. That's the only reliable way of capturing internal space station in high focal length. All right. Any further questions? I have a few, I think, questions which are asked. Quite interesting question as to what gives these colors to these nebulas and galaxies. I think there's a student who had asked these questions. Very interesting. So most of so the color is a reflection of the chemical composition. Okay, so hydrogen emits, so any object, okay, emits light in a certain wavelength. Most of the nebulas or most of the objects that you see in space are made up of, and they emit light which appears to us as red. Okay. Oxygen emits light which looks green to us. Okay. The dust, interstellar dust, absorbs light and it gives out certain light. And it produces, so when you see these colors, they are genuine colors which are emitted by these different chemicals which are present in the nebulas. Similarly, if you look at galaxies, the center of the galaxies look yellowish because these are old yellow stars. The blue stars in the spiral, which are younger stars. So the color sort of, there's a special meaning to the way you can interpret a lot of information from the colors that you see in astrophotography. That's the reason it's very important to accurately reproduce the colors that you see in your astrophotographs.
Hello. Hello.
Yes, go ahead.
Sir,
Go ahead,
I have a doubt. Can we see the meteor shower means in the pinpoint form, or the object means the real object which is going to the space means in the photos which we have clicked, the meteor shower is visible in the line form. So can we see it in the actual photo of the object?
A photo of which object? So we need to understand what causes these meteor showers. So meteors are essentially tiny bits of space rock. Okay, they're tiny. It can be as small as sort of grains of sand, which are there in space. Okay, and generally it's a result of a comet passing by, and then the debris left behind in the tail of the comet, okay, is what creates these clumps of interstellar sort of dust. And when the Earth passes through that, this material falls on Earth and it gets sort of vaporized in the Earth's atmosphere. When it gets vaporized, you see these as streaks of lights. So when we photograph and see these streaks of light, so this is actually how it appears to the eye. And this is actually how these meteors are. If you mean, can you see the meteorites which are there in space? So these are essentially dust particles. So, and dust particles, if the only reason we see them is because they, due to intense heat, they essentially get vaporized in the Earth's atmosphere. Without that, they're too tiny. They're too tiny and too faint to be captured by any camera. I hope I sort of answered that question. So if your other question is whether we can see other slightly larger objects like asteroids, yes, I mean, that's what mostly things like the near Earth asteroid study telescope does. They keep on capturing these fainter and fainter objects. That's the reason you see in news that scientists discover more as close passing asteroids. So these are essentially asteroids or rocky bodies, but not sort of they're generally not the source of meteor showers. So there seemed to have been a question there about dark matter or something. All right, I think apparently someone's trying to write something, but it's going to be hard to decipher it. I
think we should take the questions which are relevant to the topic. Dark matter, light matter, these are questions which are of different topics. So let's skip that. If anyone has specific questions, because we are running out of time. So any one or two questions maybe related to the topic. Okay. Let me just see. Rugved Mani can ask the next question. He has
what happens to the 500 rule when your camera sensor is a cropped sensor like APS-C?
That's a good question actually, because in fact that's just a rule of the thumb. As I mentioned now, it probably shouldn't be taken as 500. It probably should be taken as rule of 400. So yeah, so the crop sensor essentially, depending on what crop sensor it is. So it's Nikon, it's probably 1.5 times the focal length. If it's Canon, I think it's 1.6 or something. So essentially, you'll have less time than what that rule is giving you. So it's better to have a safety margin and probably have lesser of a shutter exposure time rather than what the rule offers you strictly. So I would recommend for crop sensor cameras, I would probably use something like a 400 rule, or even 300 if you want to get more pinpoint stars.
So
yes.
So my question is, I have a 6-inch reflector telescope with equatorial mount, but I do not have a phone tripod. So how can I use my phone with the help of telescope and take pictures of Jupiter or Saturn or some nebula or something?
Does the equatorial mount do the tracking?
No, it's manual.
It's manual. Okay, all right. Then you can take photos, but you can take photos of bright objects, essentially planets. So
yeah,
you can take photos of Moon and fine enough, even Venus. So what you would require is you require a good adapter by which you can mount your phone to the eyepiece. So I give example of a couple of ones that I'm using, but I mean they're decent ones. I mean they're not anything great. So I use a Celestron phone adapter. We call it a Celestron universal adapter. So basically you can attach your phone to the eyepiece, and you don't require a lot of exposure time to capture something like Jupiter. Definitely Saturn, it's going to be small, but yeah, that's I mean without tracking, that's probably what you would be restricted to. But you can I know a friend of mine, without a tracking telescope and using basic sort of equipment, he's able to capture some amazing views, some amazing photos of Jupiter and Saturn. So it's quite possible. All I think, but I would recommend you need to get something like an adapter, a phone adapter that you can attach your phone to the eyepiece. That's probably all that you require to begin with, at least.
So I think let's thank Amol for this wonderful session. I know there are so many questions you have, but we are actually running short of time right now. But we have created a Telegram group where you can actually post your questions. And also we have our astronomy group already created, so you can post the questions. If we find that we can keep another session of Amol maybe in the coming week. Probably we are taking this astronomy sessions as a series of lectures. So we can held another lecture of Amol for the same topic. So if any other queries are there, we will keep it. But those who want to leave can leave the meeting. Okay. So I think there are 3 more hands I can see. They can ask the questions. Thank you.
All right. I think I just saw a message sort of coming, someone typing whether how can I take star trails. So yeah. So I quickly sort of.
Yeah.
All right. So yeah. So star trails, I covered it briefly. So what happens is the simple mechanism is that you have a fixed tripod, you have a DSLR, you point your camera towards the sky, and if you're pointing your camera towards the celestial pole, you'll get these nice circular trails. Now the key is that you don't need to touch your camera. Your camera should be shooting in automatic sequence. There are certain cameras which have an inbuilt interval shooting option. Okay, so some of the Nikon cameras have this. The Canon models, to the best of my knowledge, I think they do not. So you need an external device, something called an intervalometer. The intervalometer will automate this pre-programmed sort of shooting mode. So it keeps on taking one photo or the other. So it takes one photo, let's say 20 seconds. You give an interval of, let's say, 2 or 3 seconds, then it takes another photo. Then again it waits for 2 seconds and it takes another photo. It keeps on repeating this until as long as you want. Actually, you can keep on shooting until the battery runs out or the camera SD card is full. And once that is done, you pick up all that data in your computer, and then there's a couple of very easy software to use. One is Star Stacks, Star Trails. I think I probably mentioned that in the slides, which you'll have access to. So using these, you basically all those, and then you press a button which says create a star trails, and it produces these nice circular, curvy sort of trails. It's much more easy to demonstrate than probably to talk. Probably, I think maybe we can have, as ma'am mentioned, about a workshop where this can be demonstrated.
So I wanted to ask that what is the link of the astronomy group about which ma'am told?
Yeah, so that group is actually full, and if there is a possibility of adding new people, we will do that. But for Telegram, I have already emailed everyone the link to the group. You can join that group and you can post your questions. Amol is quite active on replying all the queries which are raised. So I think let's end the meeting here. Thank you very much, Amol, for such a nice and most interactive session. You have given a wonderful information about astrophotography, and I thank Amol from behalf of Nehru Science Center and all the participants who are here. So we are ending up the meeting here. We can surely continue this discussions and the question answer sessions on our Telegram group. So let's thank Amol from our side and from all the participants. Thank you.
Yeah, thank you, everyone. Thank you. It was nice meeting you all.
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.